Hello, we are BME Design Team 2. Our project is tissue simulation with 3D printed material combinations, and we are sponsored by Stryker. So recently, Stryker purchased a Stratasys J750 digital anatomy printer, and we're interested in determining the biomimicry of its printed materials. This printer came configured with 143 preset materials, each of which vary in properties such as softness, flexibility, density, and so on. Each preset consists of a certain percentage of the base inks listed to the right, which are co-printed together to form the preset materials.
For our testing, we split up the preset materials into two groups: bone mimicking materials such as a femur mimic and tissue mimicking materials such as a liver mimic. As seen by the pie charts, the two groups of materials were split this way due to the very distinguishable differences in composition and resulting material properties. We selected 12 bone mimicking materials and 34 tissue mimicking materials to complete our testing with. The problem statement given to us by Stryker was to determine the human tissue mimicry of 3D printed materials from Stryker's digital anatomy printer. To approach this problem statement, we split it into two objectives. The first objective was to determine the effect of base inks on material properties, which was largely done through tensile testing to understand the basic material properties of the samples. The second objective was to understand bone drilling mimicry of preset materials, which was largely done through thermal imaging testing during bone drilling because Stryker has a large focus on bone materials specifically for surgical applications.
Our approach to solving this problem involved first characterizing the preset material mimics through tensile testing, hardness testing, and thermal imaging of bone drilling. Then we focused on data collection. We processed the results of the mechanical tests, which output mechanical properties such as elastic modulus and hardness. We put these values into a comprehensive database and then created a MATLAB code that allows the user to input a desired mechanical property value, and it will output the preset material as the closest match from this database. Finally, we moved into data analysis to determine the correlation between mechanical properties, as well as between base ink amounts and observed mechanical properties across the preset material mixes in each category. Lastly, we looked at application-specific comparisons between the results of our thermal tests with the bone mimicking materials and true bovine bone.
So what we found from our correlation analysis and biomimicry characterization is that an increase in the percentage of the bone matrix resulted in a decrease in the material properties of elastic modulus, ultimate tensile strength, and hardness. Similarly, an increase in tissue matrix resulted in decrease in hardness and elastic modulus. The Vero White and Agilis 30 Clear were associated with an increase in the material properties of elastic modulus and hardness as their percentages increased. Overall, the bone mimics were found to be softer, have less thermal dispersion, and lower mechanical properties compared to true bone. Tissue mimics were found to have variable mechanical properties compared to true tissue, with some of the values being extremely far off from the respective true tissue, while some were surprisingly close. Moving forward, we recommend to continue materials testing both on the rest of the presets and the bicomponent materials made out of two bases. This will help begin to define the complex relations that are forming between bases. From this testing, the expansion of the database will help pave the way to the creation of a predictive model, whether that be from machine learning or interpolation. Special thanks to the Stryker team and the biomedical engineering department at MTU.